work today. Well, at least it was sunny on the weekend.
Like rain. It's a forbidding way to start a week, though.
Yeah, well, the commute this morning was lighter. School kids aren't going to school. Other people aren't going to work. So, like positive things. So today we're going to introduce this section on matched pairs data. It's in section 3.4 of the book. We'll be looking at the earlier sections when we had two independent samples and looking at differences and testing. Today we're going to look at the matched pairs data as a special case and how you do a test, set up hypotheses for that one. The homework one that's due on Wednesday. The information on that is posted online. I'll have office hours tomorrow, kind of during a little bit of time. But if you find that those office hours don't work for you, let me know. I mean, if it's a regular thing that the office hours don't either that I had today or tomorrow. It's just not working, in a week or two, making an adjustment that helps out with the classes certainly makes sense. Okay? But any questions about anybody trying to access the R data for the assignments? Anybody have any particular problems?
It worked for me.
Worked? Good. Glad to hear it. So the idea of the matched pairs data is that much data that is gathered, right, will have a link between the first observations and the second observations. So in this diving example we're going to look at from the book, right, there's a semifinal score, and then there's a final score. So the measurements are on the same individuals, 2 at a time, and so they're obviously the same. So you can imagine that the individuals who score the highest in the semifinal, they might very well score the highest in the final, and the lowest, and then also score the lowest. So they're correlated and not independent, and if you take differences, the differences might be smaller than an average difference typically would be because of that association. Right? In many other applications, you could have some type of before measurement and after. So before you do something to individuals, you can have then a measurement happening afterward. This might be kind of a pre-test, right, and then a post-test. So in the medical examples, you have maybe baseline measurements. Right, at the start of a study or start of a procedure, set some baseline, right, and then look at change, right, that happens over time. So baseline study, and then some type of the outcome after some intervention in the middle, right? And so, because these are correlated, we're not going to do our 2-sample tests, right? And the hypothesis that you could be interested in is there a difference? There series. Is there a difference in the population at the second measurement? Right? Is there a change? And so one way to conceptualize that is in terms of the average. Is the average different? Is the average different at time 2? So the average, can be represented as that, Greek letter mu for an average difference between those two, and you might put a D on it to indicating differences. Many of the generic symbols, I like to put a little subscript or something. It kind of makes it more meaningful as to what it is. And so there are 4 steps that we use, right, to set up hypotheses and evaluate things, right? So the first one, set up hypotheses. Right? So a null hypothesis. Okay. In terms of this example, yes?
Mu sub d equals 0.
Yeah, mu sub d equals 0, right? If there is no change from time 1 to time 2 in the population, right? And then an alternative, if it's two-sided, would just be mu sub d does not equal 0. And so then we want to get a test statistic, right? So these are hypotheses, the test statistic that we could look at to evaluate this. Well, since it's about averages, we have, measurements at time 1 on, say, person I, and then measurement on time 2 at person I. And if we just simply take the differences there, d sub I, the second one minus the first one, we get the differences. And so across our n subjects, we're just going to take the average of those, right? D bars. D bar, 1 over n, the sum of I going from 1 to n of d sub I, and we get our sample averages. Right? And so we're going to get a value for our actual data set, right? Get a numerical value, and then we need to decide, is that numerical value large relative to the variation that we see in the d sub i's. Right? Small sample size, even a big deviation can be, not significant. And of course, there's a scale issue, right? Some things they might look like a big number just because it's measured in very small units. But if there's a lot of variability in the d's, then it still might not be really proof or very convincing, if you think about it, that it's like that. So we need the null distribution of the statistic. Null distribution of d bar. Right, so d bar would have a value in the data set, but if we think about, well, what would be other possible samples that we could have got if the null hypothesis is true? So how can we simulate that? Well, the null hypothesis, in this case, can be thought of as no effect, right, or no change over the time periods. So you see somebody's measurement before and after, and if there's really no change, it's just by random chance that you saw the first one here and the second one here. It'd be like measuring blood pressure. Right? You measure blood pressure twice, and if things really haven't changed, the measurements won't come out exactly the same. There's a little bit of, how you put the cuff on and how much you pump it up and how you, read it over time. And a human doing it, there's a little bit of variability. So sometimes it'll be a little higher and a little bit lower. But this null hypothesis is no effect that is completely random, which is the first and which is the second, right? So yi1 and yi2, the two measurements for a person I, are in that sense interchangeable. In the sense that you could switch them, and that'd be a perfectly valid sample under the null hypothesis. Right? So one way to generate this, right, we have to keep the measurements paired. We can't just randomly pick n observations to be the first and n observations to the other ones to be the second from all 2n because of this pairing. Right? So some people are particularly high in their values or particularly low in the values. Right? They come in this pair. So you don't want to just completely randomly scatter them. Right? There's still this linkage that if this one's in the first spot, then this one should be in the second spot. But if it were switched, which would have been the other way that it would have been seen for this person, then you'd have yi2 here or yi1 there, right? So you for each person, under the null hypothesis, right? You could have observed either yi1 as the first and yi2 as the second, or yi2 in the first spot and then yi1 in the second spot. So switching them. If we'd observe this one, we'd compute di as the difference. That, I'll put a little star. That would be kind of the hypothetical one. That's the one we actually saw. That's what actually happened. But under the null hypothesis, that's one we might have seen. On the other hand, if the other recording had done just by random chance, right, then we would have seen yi1 minus yi2, right, which would have been the reverse of that, right, because we were taking the second one minus the first one. And if this one is called di up here, this is the negative of that. So we could have just, by random chance, flipped an individual, right? That could be true for every individual. So to simulate a random sample, a new random sample under that, we're going to go through each person and just flip a coin. And if it's heads, we're going to put a negative at 1 and just keep it like it is. If it's tails, though, we're going to flip it. And kind of that accumulation overall in subjects is going to give us a new random sample. So we're going to simulate the null distribution here. So for in our, I'm writing things like I would in R, right? So we're going to go over a whole bunch of times, right? So many times. For each subject I, randomly pick a multiplier, call it m sub I, and m sub I is either going to be some number in the set of either 1 or negative 1. Right? Pick one of those two. And then we're going to let di star equal our original di times that multiplier. So if it's 1, we get the original value, and it occurs in the same order, yi1, yi2, as we actually saw. Right? But if it's negative 1, it's as if we had flipped it. And instead of seeing it would be like seeing them in reverse orders. So for each subject I, we do that, and then we're going to compute d bar of these stars. Right? We're going to take the average of these new di stars. And by doing this, many, many times here, we're going to get this sample of other averages. And under the null hypothesis, that should be centered at 0. Because every time we get a positive, we'd have a chance of getting the other negative, right? And so then we're going to look at what percent of the times the simulated average is greater than or equal to what we actually got. Or if then we get negative on things that decrease, then we're going to look at what percent of time it's below that. Right? So then we will look at the p-value. So we'll calculate a p-value then. Right? If the d bar that we have is greater than 0, right, greater than or equal to, if it's at 0, then we're not going to reject 0. So it doesn't, we don't really, if d bar is exactly 0 and it's balanced, you know, which is unlikely to happen, we're not going to reject 0 if we actually see 0. Right? But if it's greater than 0, then we're going to take the number of the simulated ones, d bars, and use an I on that, on the average, right? That are greater than or equal to our d bar, right? And we're going to divide it by the number of times that we simulate this thing. So that'll give us a fraction. And if we're looking at a two-sided hypothesis, if we just, the question we're asking, is it different, right? Then we would take 2 times that. If, on the other hand, the d bar is less than 0, right, so that on average the rankings have decreased, right? You know, bad things and, you know, elevated blood pressures, if they've gone down, or we could be very interested in a decrease. Or, you know, errors. You're counting the number of errors that are made over time, and you put in some quality improvement process. You'd hope it go down. So if our observed is less, then we're going to take the number of our the d bar stars that we simulate that are less than or equal to our observed d bar divided by the number of times we simulated. And again, two-sided, we would double that as a p-value. And so if that's small, right, if the actual value that we've seen is extreme relative to what we're able to simulate under the null hypothesis, then something's happened. Right? And generally, we'd think other things being equal, that the null hypothesis is pretty unlikely. Right? So that's the idea. So the outline, right, so we're doing with one sample. It's a matched pair sample, kind of before or after. We're taking differences. Our null hypothesis is that the average difference is 0. And we're using this little randomization trick, right, of either it could have been as we saw it, or it could have been the reverse. And that gives us new values. If we do that a bunch of times with a little algorithm, right, then we can assess that null hypothesis. Right? So let's look at it in a data example. But any questions? So I started. There it is. I started R Studio, and it started where I was last using it. Right? So it started here. My previous class was 451, so it started there. Right? And it doesn't have anything in the environment. It doesn't have the R script. Right? So I want to get to the place that I've stored my stuff. Right? So I can go down in here, and under this one for me, the statistics file, I have my 252 directories and some lectures. And so the fourth one, I want to be in this lecture space here where I have this diving data set and some R scripts. And so I'm seeing it there. I'm seeing that one, and so I would like to read it in. So I'm just diving. I'd like to just do read.csv and get that diving data set into R. And I know it has headers, so I'm going to put that. That's the default anyway, but sometimes I just like to be explicit. And it says it can't find it. Well, I see it here, but it can't find it. So R is looking someplace else, right? The working directory, it's looking, this is GETWD, gets the working directory. And it's looking at my 451 files, right? So that's where it's looking and trying to search through files. So that's why it can't find it even though I see it over here. If I go under this little click here, I can set it as working directory. So if I do that, it has done this nice command for me. It's made this thing my working directory. So now if I do the git working directory, I'm in my 252 one, and list.files. Okay, it sees the diving data set there. So if I repeat this thing, I want to highlight all of that, right? want that part, I'll just copy it down here. And it's read it in. So it's found it there. This R script, right? If I want to open that, I can click that now and it will just come up here. I think I could have just clicked at the R script and it would have popped up. But then if I tried to read in the diving data set or do things, it still wouldn't know that I really meant to be there permanently. You know, yes?
Do you have another one of the handouts?
Handouts, yeah.
Thank you.
Sorry. So yeah, that's what it did. The diving set's kind of small, right? So we can actually look at this, right? And so there was these 12 professional divers, or maybe Olympic divers from different countries, some repetitions. And in the meet, they had their semifinal score and then the final score. Right? And this is, the data that are presented. And the question could be, is there a change between semifinal and final? So it's the same person getting both of these scores, and presumably some of them are high both times. Right? Here's 360s, 382, 396, that's pretty high. A couple of these 320, 307. So they look a little bit correlated, right? You could, correlation, the correlation in this diving data set between the semifinal score and the diving data set and the final score, about 0.497, 0.5. So it's not, correlations go between -1 and 1, so 0 is uncorrelated, so that's a positive correlation, fairly strong. Right? It's not 0.99, so it's not extremely correlated, there's a lot of variability, and maybe there's just a couple outliers that decrease that correlation, but it's still a positive correlation. So we want to ask are the scores the same in the semifinal as in the final? Is the distribution of scores really the same, or is there change? And go to this one. So I'm going to create a difference column. Sometimes when you're working with data, like if you've given some data and you read it in and then you're going to do some manipulation, like delete cases or things, but then you want to be able to go back to what you did, you can create another copy. So I'm not doing anything else with this right now, but part of my practice sometimes when I do this data set is kind of back it up. Of course, if I had the original data, then I could read it in again if I wanted to start over. But I'm just, it just creates a different copy, exactly the same there. Right? Now I'm going to create a new column called difference. Right? Take the differences. So now the diving data set kind of ran off. You can move these windows a little bit, so if I do that, and then look at the data set. So by pulling the windows, it can, now we can get all 5 columns in there. Right, so these are the differences that get created. Do you think it's gone up on average or down on average?
Up.
Yeah, it kind of looks, a few people went down, but others seem to have gone up, and there's a few bigger ups that are there. If you sort the differences, right, you can see the pattern more easily in there. Up to a couple 100 observations or so, you might be able to do that. Right? If it was a big data set, head and tail give the front, part of it, and tail give the end part of it. So if you had a big data set with 500 observations, you might not want to look at the whole thing. You might want to look at the lowest ones and the biggest ones, and get that picture of it. We could even do a histogram of this. It's a fairly small number, so you could still 12 observations, 12 differences. That's kind of what the picture looks like. Right? There are some that are just below 0 or right around 0. So is it bigger than 0 or not? R has this other thing called a dot chart, which is good for little data sets. And so I, don't use this too much personally, but it gives the values along here. Right? And then it shows you every single observation. Right? First, second, third, fourth, fifth, sixth, seventh. And so you think about projecting these down, those where they would fall. So, the diving differences, let's see, dollar sign difference. There. So the first one is 72, so this is the first one. And then 13.2 is about here. The last one is negative 42, so that one is the last one here. So for small data sets. Now in some applications I've had small data sets. So when I worked with some people in speech and hearing at George Washington University, and they were dealing, evaluating children with hearing impairments or cochlear ear implants, they had a dozen children in each group, right? 2 or 3 groups, right? So you do get data sets that are important, that are 12 or 15 observations, and then you could look at individual. A lot of other ones are in the 1,000, but so the average difference is 11.975, so 11 points on average difference. Right? Relative to the data that's there, right? That's a it's a meaningful change, but is it significantly different than 0? Right? Could, if you repeated this for more divers or more meets in the same caliber of performance, would you see, scores from semifinal to final increase on average? Do they tend to go up, or is it more 0? Right? So let's simulate that, right? So we have n is the number of rows, that might be useful. Let's do something 1,000 times. Run diving. Yeah, so there we go, n. So you can check, it should have created, n should be there. There it is, it's 12, right? So there. And so we're going to do a little simulation. Yes?
What's the L next to 12?
I don't know exactly what it means there.
Is it a long?
Its value is just 12. So it's telling you something up there. So numerical, sometimes it will say character or factor or things there, but it seems to just put an L after that. Is it an integer? I'm not 100% sure. So how are we going to do the simulation, right? So for each case, we need to pick either 1 or negative 1. Right? So we have 2 values, negative 1 and 1. We want to pick n times from that. And each time we pick, we're going to do it with replacement, which means that we're going to pick negative 1 or 1 for the first one. And then we start over again, negative 1 or 1 available for the second one. We just pick one of those. Right? So we're going to pick n times from this. So for instance, what this would do is sample, well, let's look at pieces, right? So this first part here, we'll highlight that. It's just 2 values. Right? And then if I sample this with replacement, it's going to give me 12 1s or negative 1s, right? Do it again, you get another, other samples. And sometimes it flips the first one, right? So if it's a 1, the first difference, what is the first difference? Diving difference, again, dollar sign. The first one's 72. So when it's a 1, that person's going to contribute 72. Right? But when it's negative 1, it's going to contribute negative 72. It's as if that person just randomly, did better on the first or second, or just happened to flip. Under the null hypothesis, no effect. It's still drawing for that same person's distribution of scores. Right? So we're going to sample that, and then take the multiplier times the diving difference. Right? So it will take it point by point, right? And then multiply either 1 or -1, right? And then take the average of those. So each time this runs through, it gets a different sample. Right? There's a little bit of coding to make that work. Right? So we'll set a regular number seed, run through it, and here's the histogram of 1,000 values. Right? For that difference, right? And it's centered at 0 because that's the null distribution, right? Half it, if whatever positive value we have a chance of getting the other negative value by making everything, flipping every 1 to -1 and -1 to 1, and so we get the half. All right. Where's our actual one? At 11, right? At 11, there's 11. Does that look particularly extreme?
No.
It's not exactly at 0, right? But even if the null hypothesis were true, if it really was 0 difference, just by randomly picking, we could have easily got something at this point or bigger, right? It's positive, so I'll do it this way. We got 116 out of 1,000, right? So 0.116. If you double that, it's 0.232. Right? So if the alternative hypothesis is just that it's different somehow. If you had a convincing reason to say that people do better in the finals and wanted to try to convince me before doing the study that it would actually increase, you know, you could argue that it should be a one-tailed test, but I'm not, you know, totally convinced, right? So a p-value of 0.232, something happening about 23% of the time, you know, 20% is 1 out of 5, 25% would be 1 out of 4. That's not too unusual. That's easy to occur just by chance, right? And it's not going to cause me surprised in any way or to do anything else. Right? So what's the conclusion?
Statistical chance?
Yeah, it's within the scope of chance, yeah, not statistically significant. It's something that could happen by chance. And so this little data set really has not convinced us that there is an increase from semifinal to final in this study. But any questions about it? So it's like the other one, right? That we have the null hypotheses about the parameters. We're going to get a test statistic to examine it, and then we figure out this null distribution and come up with a conclusion. Right? Means are affected by, you know, outliers or a few observations. So even if we had seen a very big difference, maybe it would be because one particular person increased a whole lot. You might not want to base it, you know, have the result of a study influences so greatly. So we can change the test statistic. Right? Simulation is pretty neat that way. So if we wanted to use, say, the median as a test statistic, you know, we're still going to ask the same question: is there a difference between these two time periods? Right? So the median difference is 6.425, not quite as big. That's probably between two values, right? Because we have 12 values. So between the 6th and 7th value in terms of the differences if you sort them. So if you sort the differences. So 1, 2, 3, 4, 5, 6. So halfway between these two differences is that 6 point something, right? The 6.425 as the between the two middle battles because we're even, right? And is that significantly different from 0? So we're thinking about a population of divers in meets of this caliber, then a semifinal, and then a final, and in that population, median scores tend to go up. So we can do the simulation. I've added a 2 here because I'm going to store the results. Right? So the same name, random, same. The multiplier is the same, and multiplier times the dividing difference, and then I'm saving the median. So there's just a couple changes there to the function. Really, the median there is the big substantive change, because that gives me a new test statistic. This other business is really kind of just keeping track of things. And then I'm going to do a histogram of that and a plot, right, the histogram of that.
You didn't run it.
I didn't.
You didn't run the diffs.
Uh-huh. Thank you. Right. And so that histogram looks like that. It's not quite as smoothed out because, 12 observations. And so if you flip one to the other side, in their middle, there's kind of more of a jump, right? So you get kind of a little more boxy pattern with medians and averages. Where's our actual one? There it is. Right? Kind of similar spot, right? It's not exactly in the middle, but it's not too far in there. The difference here, 375 out of 1,000, so p-value one-sided there. The two-sided p-value is 0.75. So it's not unusual at all to get something at least this extreme or kind of on the other side, that extreme, that it would encompass about 75% of the possible outcomes. So it's pretty much right in the middle. And 0, no median difference seems plausible. Thinking about this, a little bit more, so how would you state this conclusion, right? So it's not unusual, I think, to encounter data like this. Here's this one particular meet with this excellent group of divers. How would you state a conclusion? How? What can you generalize this to? So I've been maybe giving away a little bit of my thinking about this, right? So I'm thinking about divers of this caliber and meets of this type, so what is like these individuals? And I know we don't have a lot of background on exactly what the data set is. If you read a bit more in the book, you might get a few more details of what's going on like this, right? There's often this issue of what is similar. If I am doing a medical study on impact of tobacco quitting programs, right? And I take a bunch of people at 25 different medical centers, and there's volunteers from all different ages, walks of life, and so on. And I see a big impact of a certain type of quitting program, maybe with a helpline and coaching and mailing and all that stuff. If an app comes up, that reminds you of the benefits of not smoking or something. So anything like that, and you have such a broad population, and there's thousands and millions of other people that are like that, then it's, the generalization seems to make a lot of sense, right? You hope that those people who are broadly representative of this big group. In this case, if these are the Olympic-style divers at this point in time, doing a certain meet in a foreign country, then, or in some other country under some circumstances, it's a little bit less clear what you're generalizing to. But you could maybe make a case that there is some population. It comes up a lot because people will take the entire football schedule or the entire baseball schedule and take all 28 or 32 teams or how many there are and just look at their win and loss records from this year and say, is there, between the All-Star game in the middle and the final, how did things change? Well, there's really kind of one population there. It's not really another population. But you have another season, another group of teams. You have major leagues, minor leagues. At some level that generalizes. So the statistic still is useful, I think, and kind of interesting, but it's all claiming too much for any type of test when you don't really have much to generalize to a broader population to expand to is not necessarily the wisest thing. Be a little bit more modest makes it kind of more interesting, I think.
So are you saying that we hypothetically wouldn't be able to generalize the results from this to another population?
So
or that there's a very specific population that we might be able to generalize the results to, like past and future meets with this.
Something like that, yeah. So you can think about it kind of in increments, right? So past and future meets with divers of this caliber, or maybe the next step down, like, trials. It'd be interesting to see if you took the next group of kind of trials to get into the Olympics in different countries. Do they also show this semi versus final? No. Now I would guess that at some level there's kind of an improvement. Or, a more subtle question is the people that are doing well, do they kind of improve, and the people that are not doing so well, do they get worse? Or, so there could be other things to look at. But it's, at some point, their generalization probably works, and at some point, it's stretching too far because things have changed too much. In this case, do we actually need to simulate the data? Why can we get by with not actually even simulating, not needing to simulate? Can we calculate the null distribution exactly? So,
Because there's not that many.
yeah. So simulation is fine. We did 1,000 cases, but can we do the exact null distribution? With n equals 12 individuals, with this paired design, how many possible samples are there when we're generating with this idea of flipping some of the things? How many possible samples under the null hypothesis? So samples determined for each person, right, either a 1 or negative 1, right? So there's two choices.
12 choose 2.
12 choose 2, oh no, not quite, because 12 choose 2 would be taking 12 things, and how do you choose 2 distinct ones out of that? But that is a
2 to the 12.
2 to the 12. Right? Another way of counting, right? 2 to the 12, which is 4,096. Right? So for each, there's actually 4,096 possible samples out of this. So we could enumerate all of them, right? And look at all the possible samples. And we probably are fine, and the answer's not going to change, right? Substantially, right? Whether we get a p-value of 0.35 or 0.36 or 0.40, it's still pretty big, right? But we can enumerate all 496 in this case, and I just couldn't resist. We can actually do that. This is kind of coding that's beyond what we do. Thought it, for my own interest. So I just set up a multiplier matrix, right? I'm going to take all the means, all the median values, set up this multiplier matrix. It's 4,096. And this kind of complicated stuff down here is trying to be an efficient way to get all possible strings of 1s and negative 1s, right? And this rep is something called repetition. So it repeats something. So this is, I'm going to repeat the values of 1 248 times, and then negative 1 248 times. So one possibility is going to be all, well, anyway. And this one, there's a 1,024 1s, and then 1,024 negative 1s. And then that repeats, right? So, and so on. If you're interested in the coding, we can certainly talk about what that is. We'll run through these different things, right? Let's look at what this is. The header rows of this matrix. Oops, matrix. So the first row is all 1s, right? That's going to be our sample as we saw it, right? Then the next row has all 1s except the last one is flipped, right? And then the next row, only the 11th one is flipped. And then the 12th one is flipped. Then 11 and 12 are flipped,
Yeah.
right? And then it goes to the next, that one's flipped, but these two are the same, and so on. So it's just kind of systematically going through. At the bottom of the matrix, right, it's the last row, everything is flipped. So instead of y2, y1, it's y1, y2, and so on. And then there's a difference. So it just kind of systematically goes through all those. That's coding beyond what we need to do for almost everything in the class, right? So if you go through all of those, right, and take the difference times that a particular row, right? Row is 12 things, right? So that's going to create another sample, just like that simulation. And either take the mean or median. That runs through all of them. And then the sum, the p-values would be this number. So that's just the counts, but that's out of 4,096. And so the p-value is about 0.55 for the median. Oh, wait, that's what's wrong. This is there. About 2.6 for the mean, and about 7.5 for the median. It's not completely not completely different from what we got just by our simulation of 1,000. Right? In our simulation of 1,000, it's very likely that we had some patterns repeated. So some are counting in there more than once. But that's the nature of simulation. It's fine. But we could actually do it exactly if we really thought that it was important to do so. Right? So that usually, if we had 40 cases, right? 2 to the 40th is we're not going to simulate that. We're not going to calculate all 10 to the 12th cases there. We're going to simulate 1,000 or 10,000 and use that as our basis for evaluating it. But where there's only 12, we can get all 4,096. But any questions? We have a couple other things that we're going to talk about. One thing I wanted to say is on Wednesday, we're going to look at some at chapter 4 for sampling distribution. So our statistics that we do, like y-bar or the average difference or median or something. So in general, what is the probability distribution of a statistic? Right. A statistic just is some numerical summary of data. Y-bar or sample standard deviation, sample median, etc. And so far with testing, we've been doing it under the null hypothesis. What's the distribution of values likely to, under the assumption of the null hypothesis? But chapter 4 then asks the question for other inferential purposes. In general, what's the sampling distribution? What's the normal range of variability when we're not necessarily tied to a specific null hypothesis? Right. Yeah.
Slightly unrelated. On our homework on Wednesday, on question 5, we had to do some R. Do you want us to print out that?
So some things can be printed out. You don't necessarily have to print out every detail, but if, let's say it had you do a simulation, run some code and do a simulation and report a p-value. So you can print, so since I'm providing most of the code, you can get by probably with printing a little bit less this time. If you want to print out the histogram and show where the figure is, many of the other things like the p-value and some numerical things you could just write out or write that on a sheet. So printing a page or two at most would be fine. So you don't necessarily need to reproduce all the output. And even if you do it and then you could even by hand kind of reproduce that and show where it is, and that would communicate that you've done it and looked at the graph and things like that, right? So it's good, it's fine to save some printing budget for things down the road where you're doing some of your own coding or some of your own, making some of your own graphs for displaying something, right? Since it's more scripted this time, right, you need to print less. And just as another note is that there are, eventually we will do other test procedures. Right, so for instance, chapter 8 comes back to hypothesis testing. Right? And in that chapter, we'll look at the logic that goes into things like t-tests for 1 and 2 samples, matched pairs t-tests. And so the thing that you might have seen in introductory statistics or some other classes in terms of doing tests and getting p-values from a t-distribution will come back. But for this, we want to look at this idea of the sampling distribution, the variability, and how that gets turned into inference. And so far we've done hypothesis testing with it, but we're going to eventually, well, soon after talking about that, looking at getting standard errors and confidence intervals as a method of inference, right, for that. But what I wanted to finish up with today is just thinking about matched pairs, right, studies, and what do you learn from them, right? So as so there's just a comment or two on matched pairs type of studies. So thinking about one example to illustrate this. So say you have a bunch of intersections where there's a number of accidents or there's a certain volume of traffic going through. Right, so we have intersections. Right, and you want to do a study of what impact of warning signs. So warning sign might be put up, say a new one saying there's an intersection, or caution pedestrians, or something like that, or high traffic area, or a flashing light, just different ways of doing that, something new to do that, right? So how would a matched pairs study be set up for this? Yeah.
Are you looking at like the number of accidents?
Yeah, the number of accidents
So
could be the outcome, yeah.
you'd record the number of accidents at a certain intersection before you put in the warning signs, and then after you put in the warning signs.
Mm-hmm, mm-hmm. Yep, so before, you define a time period and look at the number of accidents. Right. And then you put some warning signs in there at that point, right? And then you look after a period and you look at the number of accidents. This is supposed to say accidents here. And if the number of accidents goes down, right, you would see that change there, right? And so say you see a significant result, right? So there is a decrease. You do the simulation of the null hypothesis. There's no difference, but the decrease is a lot larger in magnitude than you typically would see under that randomization. Can you conclude then that the warning signs decrease the number of accidents? Why not?
Because it's not a causal study, you don't know what other factors might have gone into place. Like, for instance, if your before time period was in the winter, and your after time period, like the winter had passed, then perhaps the winter is contributing more to accidents than your impact, the warning sign impact.
Right. Yeah, so that's right. So if this was in the winter time when people are slipping and having all sorts of problems, and then after summertime and it's just not as much, right? There's kind of a time element, right? There's just general temporal change, going on. So weather, seasons, right? There was with the Fukushima nuclear disaster in Japan, there were studies published that had the amount of radiation detected in certain places on the west coast of the United States before the accident and then after the accident. And the claim was that the west coast of the United States was becoming radioactive because this was coming across the oceans. Well, physically, it's such a great distance, but it was at a different time. It was at a different time of year. The other funny thing is that the studies had like a real short time period here and then a longer time period over. It wasn't clear why they were using different time periods. And they were using different cities before and after. What's going on? So there's a number of problems, right? But if you searched on the internet, you would find all these places talking about it, and their one published reference was this one study. But they would quote 5 other web pages that were quoting 5 other web pages that would, talk about it. So it was all these other institutes have done it, but really at the bottom there's only one study that had this kind of temporal change or other kind of spatial changes, right? So, but this thing happens, right? So in Burlington a couple of years ago, they were studying what's the impact of bicycle lanes on accidents involving bicycles, right? So if you have the number of accidents and then it's in the news and you put in traffic, new traffic lights, traffic lanes, and you see a decrease in accident, is it caused because of that? Right? So this would be a confounding, right? All these things that are changing over the time that could affect the outcome are confounding variables. And let me try to write confounding a little bit better. Oops. Confounding. So it affects both. It's some variable that affects the outcome, the number of accidents, right? And it also is different from before versus after. So if there's more news coverage, if they put in other changes, like they repaired the roads, as well as putting these things in, then fewer potholes, people aren't swerving around as much to avoid the potholes. I'm glad they fixed the road into my neighborhood, but I was kind of getting fun to go over here, go over here, go over here. It's much safer now. But those things, it makes it hard to say causation. There's ways to do the study though, right? To set up a different type of study where you might be able to eliminate some of those impacts, right? Does anybody have any idea for? So this one is a before after, kind of pre versus post versus pre type of study, right? If you had a bunch of intersections though, and do half of them with an intervention and the other half without an intervention, right? Then you might be able to say, well, it becomes a 2-sample one, right? Each intersection, you're measuring change. There's the average change of the ones where they had that and half where they didn't, right? It costs a little bit more money, right, to monitor the data in those sites. If the big expense is putting in new warning signs and so on, or monitoring cameras or something like that, right, then it might not be that much more expensive. So the alternative then is sometimes called a comparative before after. So you could have a bunch of intersections of a certain, this pin, let's see, oops, okay, now I'm on that. I go right over here, I only want that one. Okay, that's not good. Intersections. Right. And then some of them, well, you're going to measure them all before. Right. study, and then some of them have, you know, the intervention, the new lights or the new warning signs, and then after. And then other ones, you just measure after. So if there is a change in weather from before to after, it affects both equally. If there's change in the news media, that there's awareness made because of it, affects both equally. So if this, it becomes a two-sample problem, where the basic measurement is this change, but you know, if there's a placebo type effect or just this temporal change over time, any confounding variables, they should be more equal there. And then you can talk about, well, how do you do this split into intersections? Which one should you put into there? In a public health study like this, you might only have so many streets or intersections. I mean, the Burlington area is the metro area, but it's not the biggest metro area, right? I mean, at 150,000, something like that, including all the communities, you know, it's just not huge, right? So if you had 30 intersections here, right, and that you're willing to put something on, and you're going to do 15 and 15, instead of just randomly picking 15, you might do something. Like maybe you rank the intersections by volume, right? The traffic, Vermont Department of Transportation surely has volume estimates on the largest roadways, right? Maybe volume during rush hour, volume other times, volume on weekends. So maybe you rank them, and you take the top two, right, in terms of volume, and you flip a coin. And so one of them heads, that one goes into this side, and tails, it goes into that side. So now you have your two largest intersections, one that's getting treated and one that's not. Right? And you keep going down. So that out of these 30, the smallest of those 30 big intersections, right, what is on one side and the other. And if you flip that coin, then it's kind of fair, like a randomized experiment. Right? So you're kind of a matched pairs within a before-after comparative type of study. Right? But that controls the factor of size. So it's not just the big ones or the ones that the alderman or city council person makes the biggest point. You got to put one in my area, right? It's not influenced by that, and it controls for confounding. So these designs and things that look at face value is pretty ordinary. You know, actually using them effectively takes a little thought, and there's some design behind it that's a little bit more complicated. But in the end, however you're doing it, we're going to try and think about generating, you know, having some test statistic, generating the null distribution. The more complex these designs become, the more a little bit complicated our simulation has to become. Or there's kind of more assumptions that we got to think about. And we'll kind of build up towards some of these things in terms of analysis as we go on. But that's basically what right? Again, I'll have office hours. The other, you know, so you'll notice things about, so Friday is math department's student summer research projects presentations. So Friday, 3:15 in Charade. And so a number of individuals from math statistics will be talking about some of the group, about things that they've done. And so I encourage you to look for that and attend that seminar, if at all possible, to see a variety of things. All right. Hi.
Hi.
Yes.
I don't know what's the homework.
There's a homework post on Canvas. Have you accessed to Canvas?
I don't have
Yes.
access.
So let me send that to you. What's your email?